So let's go quickly to the answers. Piezoelectric materials are piezoresistive. Always, have, never, or sometimes. No, never. The reason for that is that piezoelectric materials have to be ceramic materials. And piezoresistive materials have to be semiconductor materials. And a semiconductor can never be ceramic. A ceramic is a dielectric, is not conducting. A semiconductor must conduct. So they can never be, because these have to be these fundamental materials, they can never be the same at the same time. Piezoelectric material can never be piezoresistive, and the piezoresistive material can never be piezoelectric. How can I think this? Well, imagine that, for example, my piezoelectric material would be a semiconductor or a conductor. Well, if I'll put a voltage over a conductor or a semiconductor, what happens is that my electric field will be zero, because I'll have a pure conductor. So it will be impossible for me to put a piezoelectric field, an electric field over it, and it will be impossible for me to change, because I have no field. I cannot move any atoms in any lattice that would be available. On the other hand, if a piezoresistive material would be ceramic, it would not be conductive, and therefore it would not be resistive at all. It would have an infinite resistivity. So I would not be able to use it as a resistor. Let's look at the third statement. Piezoresistive materials can be used as sensor materials. Yes, of course, they can. We've shown that they can be used as strain gauges, but also as thermal sensors. Fourth statement. Piezoresistive materials can be used as actuator materials. No, they can not per se. The piezoresistivity does not generate any motion. It's a change in the band structure of the material. It's not changing any motion. So no, you cannot use them as actuators. Piezoelectric materials can be used as a sensor material. Yes, they can. So, for example, if I will deform a piezoelectric material, I will generate a voltage over it, and that voltage I can take out and use it as a sensing of the deformation. So yes, I can. The loudspeakers that I showed can also be used actually as a microphone, and in that sense they are a sensor. The sixth statement is piezoelectric materials can be used as an actuator material. Yes, they can. That's why we show them here. So if you put a voltage over them, they will deform, such as in a loudspeaker. So we note that piezoelectric materials can be both sensor and actuator, so they can be used in both directions for transduction. Piezoresistive materials cannot be used in both directions, so they can only be used as a sensor, but not in the opposite direction. And that's actually an interesting question in physics you can ask yourself. Why is the piezoelectric material kind of, you can reverse it, but why can you not do that with a piezoelectric material? What is the fundamental reason behind that? And if you think about it, probably it has to do something again with entropy. But I let that up to you to think about. Now we're going to look at piezoelectric materials. When would you use them in MEMS or in general? Again, as an engineer, sometimes you'll have to make a decision. You're going to use a magnetic, electrostatic, thermal, or piezoelectric actuator. Well, piezoelectric actuators, they are very fast. Why is that? Well, if you put a voltage, the effect is immediate. So you put a voltage over a piezoelectric crystal, it will immediately transform. It's like basically, it's like loading it. A piezoelectric actuator is, from an electrical perspective, is a capacitance. You have two plates with the dielectric in between. So the system will respond as fast as a capacitor would respond. So if I have, that's very fast. Also, they have a low energy consumption. Again, if you see it as a capacitance, the only energy consumption you have is basically the loading and unloading of the charges to the piezoelectric material. It has a very high force output. If you put a voltage, it will be forced to deform. It will be very difficult to stop that deformation. And it is very linear. It will deform linearly with the voltage applied. On the negative side, you do require very high voltage to create a very small, to only get a very small deformation. You had the factor 10 to the minus 6 there. Of course, there's ways around it. For example, using it as a bimorph, you can get around that to some extent, but still, you need a very high voltage, typically 100 volts or more. And so you need to have that kind of power at your microsystem if you want to use it in a microsystem. It's complicated for batch manufacturing. These crystals, they are really bulk materials. There are a few approaches to integrate them on CMOS, but they only create very thin layer. They're very expensive methods, and they're not very high quality piezoelectric materials. So again, typically you're going to take a batch macroscopic material and then integrate that to the microsystem on a piece per piece, by, for example, by gluing, which makes it expensive. It's limited to temperature, typically below 100 degrees, and that's due to the Curie temperature. The material will depole. There are some piezoelectric materials that have a Curie temperature up to 600 degrees, but they are more expensive and they're very specific. Also, at higher temperature, you will get, typically because with integration, you'll need to glue on your piezo to your microsystem, and at high temperatures, your glue may soften, which is a very actual problem. And again, you have a very low displacement. So we're going to have a look at some examples. One field, you're going to see that in RF MEMS, radio frequency MEMS. You're going to have a lecture on just radio frequency MEMS, but they're going to show you already one example here, where they're used in F-bar filters. That means film bulk acoustic resonators. Here, piezoelectric materials are used to filter high frequency, typically like gigahertz frequency electronic signals. And typically that is used in filters in mobile telephony. And why would you do that? You get an incoming signal, for example, from an antenna. So it's an AC signal with a very high frequency. Your piezoelectric material, then you put that signal over a piezoelectric material. What happens is that piezoelectric material will start resonating. So you convert your electrical signal to sound, but in the gigahertz range or the higher megahertz range. That is an acoustic signal that travels to the material. And then at the other side of the material, you can pick it up again by two electrodes. And so here you use it as an actuator and here you use it as a sensor. And here you pick up your signal again and you get an electronic signal. However, you can shape the geometry of your piezoelectric material as such that the sound waves that are created in here can only be up, for example, a certain frequency. So you can build basically a filter. Only certain frequencies will be allowed. Will be the sound. How would I say? The sound signal will only be traveling to the material at certain frequencies and other frequencies not. So basically, you will filter out your beginning signal. You will filter out specific signals, and you only get specific signals through here. So this is for filtering an electronic signal. Another example. This is an upcoming field in MEMS for the past 10 years. There's more and more work in energy harvesting MEMS. The idea is that you make small systems that pick up energy that's available in the surroundings and that is transferred to to power, for example, a small sensor that then does not need, for example, a battery or an electrical connector for power. An example is here, for example, running shoes with little LED lights. So you see that sometimes on kids' shoes. Every time they step, you see the little LED light in the shoe that lights up. Here there's a cartoon of such a shoe, where you can see there's two yellow piezoelectric generators and one battery. So what happens is that you make a piezoelectric bimorph, and that is fixed on one side, and the other side has a proof mass, an inertial mass. And as you're walking, every time you step, this mass is moving up and down, and that generates a voltage over the piezoelectric yellow layer. Here's a piezoelectric layer, generates a voltage, and that voltage is then sent to an electronic rectifier, and then used to load a battery. There are numerous other applications of piezoelectric transducers. This is from a paper from end of the 90s, but still it gives a good idea already where we can see it. It's used in, for example, in PMUTs. It's piezoelectric micromachined ultrasonic transducers. You use it sometimes in micropumps. You use it for manipulation of small particles, etc., etc., etc. I'm not going to go through all these applications. You can search yourself for more applications. Good starting point is either looking at this paper from Angus I. Kingan, or you go simply on Wikipedia, search to this address piezoelectricity, or you look at the site www.piezomaterials.com, where you find a lot about both the materials and its applications.